Welding is a fabrication process whereby two or more parts are fused together by means of heat, pressure, or both, forming a joint as the parts cool. Welding is usually used on metals and thermoplastics. The completed welded joint may be referred to as a weldment. Some materials require the use of specific processes and techniques. A number are considered unweldable. Weldability is defined by the American Welding Society, AWS, as the capacity of a metal to be welded under the fabrication conditions imposed into a specific suitably designed structure and to perform satisfactorily in the intended service. Or simply, weldability of a metal is the ability or the ease of the metals with which two similar or dissimilar metals are joined. The parts that are joined are known as a parent material. The material added to help form the join is called filler or consumable. A filler material may or may not be added to the joint to form a completed weld joint. Autogenous welds are formed without adding filler material to the joint. Heterogeneous welds are formed when the filler material added is of different composition as that of the base metal. Homogeneous welds are formed when the filler material added is of the same composition as that of the base metal. The completed welded joint may be referred to as a weldment. Uses and applications of welding: automobile construction, railroad equipment, ship construction, aircraft construction, building construction, bridges construction, pressure vessels, storage tanks, piping and pipelines, fabrication of jigs, fixtures, and machine tools, repair of broken and damaged parts, household furniture, material handling equipments, etc. Selection of the welding joining process. The selection of the welding process for a particular job depends on many factors. No one specific rule controls the welding process to be selected for a certain job. The following are a few of the factors that must be considered when choosing a welding process. Availability of equipment. The types, capacity, and condition of equipment that can be used to make the welds. Repetitiveness of the operation. How many of the welds will be required to complete the job, and are they all the same? Quality requirements. Is this weld going to be used on a piece of furniture, to repair a piece of equipment, or to join a pipeline? Location of work. Will the weld be in a shop or on a remote job site? Materials to be joined. Are the parts made out of a standard metal or some exotic alloy? Appearance of the finished product. Will this be a weldment that is needed only to test an idea, or will it be a permanent structure? Size of the parts to be joined. Are the parts small, large, or different sizes, and can they be moved or must they be welded in place? Time available for work. Is this a rush job needing a fast repair, or is there time to allow for pre-weld and post-weld cleanup? Skill or experience of workers. Do the welders have the ability to do the job? Cost of materials. Will the weldment be worth the expense of special equipment materials or finishing time? Code or specification requirements. Often the selection of the process is dictated by the governing agency, codes, or standards. The welding engineer and/or the welder not only must decide on the welding process, but also must select the method of applying it. The following methods, manual operation, semi-automatic operation, machine operation, automatic operation, and automated operation, are used to perform welding, cutting, or brazing operations. Manual. The welder is required to manipulate the entire process. Semi-automatic. Filler metal is added automatically and all other manipulation is done manually by the welder. Machine operations are done mechanically under the observation and correction of a welding operator. Automatic operations are performed repeatedly by a machine that has been programmed to do an entire operation without interaction of the operator. Automated operations are performed repeatedly by a robot or other machine that is programmed flexibly to do a variety of processes. Advantages of welding. A good weld is as strong as the base metal. A large number of metals alloys can be joined by welding. C. Repair by welding is very easy. D. Welding can be easily mechanized. E. Portable welding equipment is available. F. General welding equipment is not very costly. G. Total joining cost is less in case of welding joint. Disadvantages of welding. A. Welding produces the harmful radiation, fumes, and spatter. B. A skilled welder is required. C. Welding heat produces metallurgical changes. D. Cost of equipment, initial cost is high. E. Edge preparation is required before welding. F. More safety devices are required. G. Jigs and fixtures are required to hold the parts to be welded. Welding processes. Welding processes differ greatly in the manner in which heat, pressure, or both heat and pressure are applied and in the type of equipment used. There are over 100 welding processes, but the most popular ones are as follows. Shielded metal arc welding, SMAW, often called stick welding. Gas tungsten arc welding, GTAW. Gas metal arc welding, GMAW. Flux cord arc welding, FCAW. Gas welding, resistance welding, submerged arc welding, 1. Shielded metal arc welding, SMAW. Shielded metal arc welding, SMAW, uses a consumable stick electrode that conducts the welding current from the electrode holder to the work, and as the arc melts the end of the electrode away, it becomes part of the weld metal. Stick electrodes are of different sizes gauges. The welding arc vaporizes the solid flux that covers the electrode so that it forms an expanding gaseous cloud to protect the molten weld metal. In addition to fluxes protecting molten weld metal, they also perform a number of beneficial functions for the weld, depending on the type of leg being used. SMA welding equipment can be very basic as compared to other welding processes. It can consist of a welding transformer and 2 welding cables with a work clamp and electrode holder. Figure 1.9. There are more types and sizes of SMA welding electrodes than there are filler metal types and sizes for any other welding process. This wide selection of filler metal allows welders to select the best electrode type and size to fit their specific welding job requirements. Therefore, a wide variety of metal types and metal thicknesses can be joined with one machine. 2. Gas welding. Gas welding is a metal joining process in which an oxy-fuel gas, fuel gases, and oxygen are used to weld and cut metals. In gas welding, a high-temperature flame is produced at the torch tip by burning oxygen and a fuel gas. The most common fuel gas is acetylene. However, other combinations of oxygen and fuel gases can be used for welding, such as hydrogen, MAP, or propane. An oxy-fuel gas flame heats the base metal to a sufficient temperature but below its melting point so that a filler wire can be melted and bond to the hot base metal. The base metal is heated, and a filler metal may be added to reinforce the weld. A flux may be used to help the filler wire metal to sufficiently bond to the base metal. Gas welding processes include brazing and soldering. Brazing occurs at a temperature above 840 degrees Fahrenheit, 450 degrees Celsius, while soldering takes place at temperatures below 850 degrees, but both uses the same equipment and a similar process. Brazing versus soldering. Brazing. Soldering occurs at a temperature above 840 degrees, occurs at temperatures below 840 degrees, 450 degrees Celsius. Joints are stronger. Joints are weaker. Brazing is more expensive, soldering is less expensive. More close fit joint is required, less close fitting is required. Used in metal joining, but can also be used in electrical industry to join electronic components. 3. Gas tungsten arc welding, GTA tungsten inert gas welding. Gas tungsten arc welding, GTAW, is also known as tungsten inert gas welding. Welding uses a non-consumable electrode made of tungsten. In GTA welding, the arc between the electrode and the base metal melts the base metal and the end of the filler metal as it is manually dipped into the molten weld pool. A shielding gas flowing from the gun nozzle protects the molten weld metal from atmospheric contamination. Inert gases like argon, helium, or a mixture of the two is used for shielding. Even though GTA welding is slower and requires a higher skill level as compared to other manual welding processes, it is still in demand because it can be used to make extremely high-quality welds in applications where weld integrity is critical, and there are metal alloys that can be joined only with the GTA welding process. 4. Gas metal arc welding, GMAW, metal inert gas, ME, and metal active gas, MAG, welding. Gas metal arc welding, GMAW, is a broad classification for various gas-shielded metal arc welding processes, that is, MIG and MAG. The main difference between the two GMAW processes, MIG and MAG, is the shielding gas used. When an inert gas like argon or helium is used, the process is called MIG welding and MAG welding. When an active gas like carbon dioxide, CO2, or a mixture of CO2 and argon or oxygen. Gas metal arc welding, GMAW, uses a solid electrode wire that is continuously fed from a spool through the welding cable assembly and out through the gun. A shielding gas flows through a separate tube in the cable assembly, out of the welding gun nozzle and around the electrode wire. The welding power flows through a cable in the cable assembly and is transferred to the electrode wire at the welding gun. The GMA weld is produced as the arc melts the end of the continuously fed filler electrode wire and the surface of the base metal. The molten electrode metal transfers across the arc and becomes part of the weld. The gas shield flows out of the welding gun nozzle to protect the molten weld from atmospheric contamination. GMA welding is extremely fast and economical because it can produce long welds rapidly that require very little post-weld cleanup. This process can be used to weld metal ranging in thickness from thin gauge sheet metal to heavy plate by making only a few changes in the welding setup. Other welding processes include submerged arc welding. Submerged arc welding is an arc welding process that involves the formation of an arc between a continuously fed electrode and the workpiece. A blanket of powdered flux generates a protective gas shield and a slag, and may also be used to add alloying elements to the weld pool, which protects the weld zone. When molten, the flux becomes conductive and provides a current path between the electrode and the work. This thick layer of flux completely covers the molten metal, thus preventing spatter and sparks, as well as suppressing the intense ultraviolet radiation and fumes that are a part of the shielded metal arc welding (SMAW) process. The welding head moves from right to left. The flux powder is supplied by the hopper on the left-hand side, then follow 3 filler wire guns, and finally a vacuum cleaner. Resistance welding. Resistance welding is a group of welding processes in which heat for welding is obtained from the resistance of the workpiece, metal, to the flow of electric current and with the application of pressure. No filler metal or flux is added. In resistance welding, both heat and pressure are used to make the joint or establish the coalescence. Types of resistance welding: A. Spot welding. B. Seam welding. B. Projection welding. C. Resistance butt welding. D. Flash butt welding. E. Percussion welding. Applications of resistance welding: joining of sheets, bars, tubes, making of metal furniture, making fuel tanks of cars, tractors, making of containers, welding aircraft and automobile parts. Resistance spot welding. The electric resistance spot welding process is shown in figures. Electrodes 1 and 7 presses against workpieces 3 and 5. A current is then passed through these components. Because of the electrical contact resistance, heat will be generated at electrode workpiece interfaces 2 and 6 and faying mating surface 4. The heat at the faying face melts the workpieces to form a nugget 4. To prevent melting at the electrode workpiece interface, water is circulated in the cooling chamber of the electrodes. Spot welding. Spot welding is a resistance welding process in which overlapping sheets are joined by local fusion at one or more spots by the heat and pressures applied by the electrodes, one above and other below the workpieces. The heat is generated because of the resistance to the flow of electric current through workpiece. Seam welding. Seam welding is a resistance welding process in which overlapping sheets are joined by local fusion progressively along a joint by 2 rotating the circular electrodes. Fusion takes place because of heat, which is generated from the resistance to electric current flow through the work parts, which are held together under pressure by electrodes. Projection welding. Projection welding is another advancement of spot welding, where one of the sheets to be joined is provided with a number of projections to help localize the current at a predetermined spot. Thus, the surfaces of the workpieces are in contact with each other only at the projections. Percussion welding. In this resistance welding, welding heat is obtained from an arc produced by a rapid discharge of stored electrical energy. Pressure is applied rapidly during and immediately following the electric discharge. The electrostatic capacitors, condensers, are used to store the electrical energy. Resistance welding types. Summary. C. Plasma arc welding. W. This is a fusion welding process that uses a non-consumable electrode and an electric plasma arc to weld metals. Just like TIG welding, its electrode is tungsten-based, thoriated tungsten, but its torch is designed differently and provides a more focused beam than TIG. Metals like stainless steel, aluminum, copper, and bronze can be welded.